It probably helps the X-37B spacecraft is comparatively tiny. 2 of them could fit in a now retired space shuttle's payload, so they're easier to get into orbit.
Go back to the story we were telling you about, the secretive project blasting off from the Kennedy Space Center.
The Space Force says that the mission launching this weekend will test new orbital regimes, traveling further out than any other of the previous missions for the space plane.
In the silent domain above our heads, invisible to the untrained eye, one machine has redefined the possibilities for technological testing and experimentation in space. It's not a legend, nor a fragment of science fiction, but a reality. America's X-37B spaceplane. For more than a decade, this unique craft has circled above, always uncrewed, methodically returning to Earth with the calm precision of a commercial jet. With each return, curiosity intensifies. The X-37B's record is singular in American aerospace. More than 1.3 billion miles traveled, thousands of days spent in low Earth orbit, 7 completed missions, all without a pilot on board. Every deployment, every re-entry is meticulously scheduled, but only partly revealed to the public, prompting extensive analysis and speculation. Why does the United States invest in such a platform? One that can remain in orbit for years on end, conducting missions largely shielded from public view. What are the Space Force and Air Force seeking to accomplish with a craft whose technical details and mission payloads are often classified? The X-37B stands as a paradigm-shifting testbed, functioning at the forefront of American space experimentation and capability development. Tonight, we'll look closely at the documented facts, public statements, and known technical achievements that define America's most actively guarded spacecraft. The story of the X-37B offers insight into American priorities in the orbital domain, and its ongoing missions outline a steady evolution in space technology. In an era where space is increasingly vital to both national security and technological leadership, the X-37B serves as a signal of ongoing change. The architecture of secrecy, uncrewed, reusable, relentless. The X-37B, formerly known as the Orbital Test Vehicle or OTV, is an uncrewed, reusable spaceplane developed by Boeing for the US government. Its silhouette recalls a scaled-down version of the retired NASA space shuttle, but similarities end there. Unlike the shuttle, the X-37B is designed exclusively for robotic flight, carrying no astronauts, only technology experiments and equipment destined to undergo rigorous testing in the harsh environment of space. Launching atop a conventional rocket, the X-37B is propelled into orbit before separating and beginning its autonomous flight phase. From this point, the spaceplane operates entirely without human presence on board, executing a suite of programmed operations and carrying out carefully selected payload experiments. After an extended period in orbit, often exceeding a year, and sometimes approaching 2, the craft autonomously re-enters Earth's atmosphere, glides to a precise runway landing, and is then secured for analysis and refurbishment. As of its latest completed mission, the X-37B fleet, currently encompassing 2 operational vehicles, has completed 7 successful flights. Each mission has gradually increased in duration and complexity, with the total time spent in orbit reaching thousands of days and the distance covered surpassing 1.3 billion miles. This impressive resume stands as a testament both to American engineering and to the reliability required for genuine progress in reusable spacecraft. Despite these public metrics, the program is among the most closely managed in the Pentagon's portfolio. Details on the X-37B's operations are released only in general terms. Most information about its payloads, flight paths, exact durations, and onboard technologies remains classified. What is clear from official channels is that each flight is designed to extend the limits of what is feasible, producing data and experience that inform the future of American space operations. What motivates such a high degree of secrecy? While speculation abounds, the available facts support several well-established objectives. A platform for experimentation, the strategic laboratory in orbit. Official statements and press releases from the US Space Force confirm that the X-37B is primarily a technology testing platform, unlike satellites that are confined to specific, unchanging missions, or human crews that are limited by size and duration constraints, the X-37B is built for flexibility. Each flight typically carries a set of technology demonstrations, often selected by different U.S. government agencies. The vehicle's cargo bay can accommodate multiple experiments, which are mounted and integrated for flight testing in the real conditions of space. These technology demonstrations can vary in focus, but recent flights have reportedly included advanced laser communication systems. Such technology aims to provide high bandwidth, secure data transfer from orbit, an important advance for both military command and control, and the future of commercial communications infrastructure in space. Another area of experiment involves quantum technologies. Though the specifics are not publicly released, quantum experimentation is considered highly sensitive and cutting-edge. Its inclusion aboard the X-37B suggests a focus on improved security, data processing, or other breakthrough capabilities. The X-37B's ability to recover its payloads after extended spaceflight provides a rare opportunity for forensic analysis of hardware that has faced real-world orbital hazards, valuable data that can't be fully replicated in ground-based testing. This unique recoverability is a hallmark advantage of the X-37B. Unlike nearly all satellites, which are committed to their orbits as long as they function, and ultimately burn up in re-entry, the X-37B delivers both itself and its experimental cargo safely back to Earth. This allows engineers and scientists to examine the precise effects of extended space exposure, radiation, thermal cycling, micrometeoroid impacts, and more. The range of experiments conducted is broad. Past missions have included work with advanced materials, research on new propulsion techniques, and the exposure of biological samples to microgravity and radiation. In some cases, components tested and iterated aboard the X-37B may lay groundwork for future generations of operational satellites, communications gear, or other spacecraft. This accelerates the innovation cycle. What's learned from one mission can be applied to the next with minimal delay. This adaptability is central to the X-37B's value. The program enables the US to trial new capabilities, harden systems against the unpredictable conditions of space, and iterate at a pace not possible with single-use satellite platforms. Such advantages have clear relevance in a context where technological supremacy and reliability in orbit are of national interest. Endurance, maneuverability, and the demonstration of capability. Among the most notable achievements of the X-37B are its endurance and maneuverability. The spaceplane is capable of remaining operational in orbit for durations exceeding a full year, significantly longer than any current human-crewed vehicle, and well beyond the requirements for most single-mission satellites. Long missions allow for extended data collection, thorough stress testing, and the opportunity to observe the evolving condition of technologies under real spaceflight conditions. The X-37B is also capable of changing its orbit during flight, supporting a broader range of experimental scenarios and data collection. This orbital maneuverability provides opportunities for expanded testing and the demonstration of techniques unattainable by fixed-path satellites. One of the most significant technical milestones in recent years was the public disclosure that the X-37B executed a novel aerobraking maneuver. According to a Space Force press statement, the spaceplane made multiple controlled passes through the upper layers of Earth's atmosphere to alter its velocity and orbit. This sophisticated maneuver, traditionally used by planetary probes and rarely attempted with reusable spacecraft, enables adjustments in mission profile without relying heavily on stored propellants. It demonstrates both the confidence US planners have in the X-37B's design and the desire to maximize operational flexibility. The autonomy of the X-37B should also be highlighted. Unlike early space vehicles that depended heavily on real-time control from ground operators, the X-37B possesses advanced onboard navigation and guidance systems. These permit the vehicle to make critical decisions and adjustments on its own, including real-time re-entry course corrections, which significantly enhances mission safety and reliability. As a result, the spaceplane can execute complex flight and landing operations autonomously, reducing vulnerabilities and extending mission capability. Together, these technical attributes, endurance, maneuverability, and autonomy, underscore why the X-37B has been adopted as a primary platform for the evolution of American space experimentation. The X-37B and the evolution of space operations. The X-37B's operational model marks a shift from traditional space asset deployment. Whereas satellites are placed in fixed orbits with predetermined mission parameters, the X-37B introduces both ambiguity and adaptability into U.S. space operations. Its flight profiles, the duration of missions, orbital inclinations, and re-entry dates are rarely published in advance and often only partially disclosed after completion. This inherent unpredictability complicates efforts by other nations or outside observers to anticipate or counter U.S. activities in orbit. Just as important, the payload capacity and modular cargo bay design allow for rapid changes in mission focus. Lessons learned from one flight can directly inform the composition, goals, and preparations for the next, with minimal lag between cycles. In contrast, traditional satellites are often obsolete by the time they are decommissioned, as functional improvements are constrained by long ground-up development timelines. The recoverability of systems and experiments grants the U.S. a unique analytical advantage. Each recovered payload, subjected to comprehensive post-flight evaluation, may yield insights that feed directly into the broader American satellite constellation. The X-37B effectively serves as a testbed for next-generation sensors, communications links, materials, or guidance systems that may later be fielded in regular operational satellites. For every experiment or mission profile that is made public, the contents of several other payloads remain undisclosed. This ambiguity, in itself, creates strategic complexity. Adversaries must reckon with the possibility of ongoing experimentation, or the presence of as-yet unseen operational capabilities in orbit, an environment where uncertainty can be as effective a deterrent as overt capability. Operating under such secrecy, the X-37B program introduces an element of unpredictability to U.S. space capability development. Upgrades, adjustments, and expanded objectives can be implemented on short notice, should the security landscape shift or new technical needs arise. This responsiveness is a significant advantage in a volatile and rapidly evolving global context, the nexus of technology and national security. The X-37B has taken on a significant symbolic role in communicating American priorities and intent in space. Its achievements are visible, even if their particulars are not fully detailed. Successfully completing extended duration missions, returning to Earth for direct analysis, and integrating new technology with each flight all send a clear signal. The United States is committed to maintaining and advancing its position at the cutting edge of space operations. The suite of experiments the X-37B hosts, such as advanced laser communications or quantum technologies, underlines a focus on secure, resilient information transfer, robust command and control structures, and the overall hardening of space-based assets. These areas directly underpin national security, both in the context of global competition and in maintaining the reliability of the infrastructure modern society depends upon. Components returned from orbit are examined for subtle failures or performance shifts induced by spaceflight, helping engineers understand how innovations fare under true mission conditions. This empirical, real-world feedback shortens development cycles for future platforms, yielding more reliable hardware and expanding American capacity for high-stakes operations in space. For America's strategic competitors, the existence and ongoing success of the X-37B operates as a form of pressure. Its visible evolution has motivated other nations, including China and Russia, to dedicate resources to similar reusable or retrievable spacecraft. This indicates not only the recognition of the platform's value, but also a growing understanding that future leadership in space will require mastery in reusability, rapid iteration, and orbital flexibility. Mastery of the long game, what each mission achieves. Across 7 completed flights, the X-37B has accumulated a body of operational data and technical progress that is both substantial and, in many respects, unprecedented. Each new deployment has included incremental upgrades and expanded mission profiles, longer time in orbit, more complex experimentation, and increasingly refined flight operations. The stepwise increase in mission duration indicates ongoing confidence in the hardware and systems. What began with relatively modest test flights has evolved into multi-year stints in orbit, with each mission expanding the operational envelope a little further. Alongside test hardware, new classes of research, ranging from communications payloads to advanced shielding and biological sample exposure, have reflected a broadening and deepening of focus. The steady progress of the X-37B in mission length and experiment complexity speaks to a program designed for continuous improvement. By integrating new technologies and objectives each flight, the X-37B ensures that advancements made in the laboratory can be validated quickly in the unforgiving environment of spaceflight. Further, the spaceplane's capacity for advanced flight maneuvers, like aerobraking, highlights the technical sophistication being developed and tested. Such capabilities, once proven, influence future designs for everything from satellite repositioning to the management of orbital debris or even planetary exploration. Cost benefits associated with reusability cannot be overlooked. Each mission that successfully returns the vehicle and its experimental payloads provides value for subsequent operations, and lessons learned are incorporated into both military and civilian spacecraft development. This iterative process contributes materially to the advancement of the broader space sector. A glimpse behind the veil, the limits of public knowledge. Though much remains classified, the X-37B's public record dispels some myths. Contrary to popular suggestion, the vehicle's primary role is not as an orbital weapon or crewed transporter. Instead, its mandate is to expand the U.S. technological edge through structured, recoverable experimentation under the auspices of the Space Force and Air Force. The approach to risk, cost, and evolution is markedly different from traditional satellites. Because hardware can be recovered, tested, repaired, and reflown, tolerance for failed experiments is higher. Each cycle offers an opportunity to try new ideas, turning space into a routine rather than exceptional domain for technological innovation. The experimental focus of the program, highlighted by well-documented lines of research such as advanced communication and maneuvering technologies, is neither accidental nor merely scientific. These relate directly to operational requirements in the military space domain, including the need to secure information flows, avoid interception or jamming, and sustain operations in contested environments. The visible record of achievement, successful landings, growing mission durations, and technical milestones like aerobraking demonstrates that the X-37B is indeed providing a measurable benefit to American space capability. As America's public and private interest in space accelerates, the X-37B underscores that developments in orbital hardware, materials, and techniques often originate in military or governmental research and are only later adapted for commercial or civilian purposes. This cross-pollination continues to shape the evolution of space technology worldwide. The ripple effects in the international arena. The X-37B's successes have been noted worldwide. As the platform returns from one mission and prepares for another, its documented achievements become subjects of close study by foreign governments, policy analysts, and technical experts. For rival states, the absence of operational detail compels efforts to monitor, develop countermeasures, or match capabilities, an inevitable dynamic in technology-driven competition. Beyond direct defense considerations, the X-37B is reshaping broader expectations for what is achievable in space. Its routine demonstration of reusability and recoverability sets new standards for reliability, flexibility, and the rate of innovation. Concepts such as on-orbit servicing, rapid mission turnaround, and flexible deployment are becoming increasingly important for planners in both governmental and commercial sectors globally. This evolving environment places pressure on other nations to pursue similar advances or risk lagging behind. As mastery of adaptive and robust technology becomes more central to strategic influence and deterrence, the cycle of experimentation and iteration the X-37B demonstrates becomes a widely studied model. The presence of the X-37B has spurred international discussion on the need for agreements and protocols relating to reusable and maneuverable space vehicles, as well as questions about transparency and the militarization of space. The boundaries between peaceful technological progress and implicit military capability have become increasingly blurred, with the X-37B program exemplifying the challenges facing policymakers in the years ahead. The landing and the legacy. When the X-37B completes another flight, silently descending and executing a precise landing on a terrestrial runway, it marks not only the end of another mission, but also an ongoing process of evaluation and renewal. The lessons learned from each recovery are incorporated into future deployments. Each successful return builds upon the cumulative knowledge base, gradually strengthening American capabilities in the most difficult operational environment known. Every payload brought back is examined for successes and challenges, updating the playbook for future missions. This cycle of launch, in-orbit operation, return, and assessment becomes the rhythm of American progress in space. In total, the X-37B program stands as a reminder that real innovation is often gradual, fostered by repeated testing, recovery, and improvement. Its ongoing flights are a visible sign that the U.S. recognizes both the complexity and opportunity inherent in the space domain. The program does not seek spectacle. Rather, it illustrates a deliberate, measured approach to capability development built on confirmed technical achievement. The real story of the X-37B is not one of secret weapons or dramatic breakthroughs, but of a structured, disciplined pursuit of mastery in orbital operations. It demonstrates that progress in space is conditioned by willingness to test, learn, and evolve rapidly, factors that are critical in the context of shifting technological and security demands. As the X-37B continues to fly, land, and launch again, it outlines a path forward in which mastery in space will be determined not by dramatic gestures, but by the steady, reliable accumulation of technological and operational advantage. In this, the X-37B has become both a model and catalyst for the next era of space exploration, experimentation, and security. The ongoing presence of the X-37B points not to a hidden agenda, but to the reality that the landscape of space power is changing. And with each mission, America's capacity to adapt and refine its presence on the final frontier only grows stronger. As the X-37B lifts into orbit once more, it is the patient, silent work of innovation and exploration that carries the United States further, setting the pace in the long contest for mastery above our world.